This video looks at constrained optimization. This will be a really simple example. It's an example we can graph so we can see how it works, but it'll go into some of the mathematics in a very kind of high level stylistic way about how you can optimize a function. But the really important thing here has to do with the constraint. So this is one of a series of videos. The first one is just a simple example of constrained optimization where we have a quadratic function with one variable, and gets into some of the issues of what happens with the constraint. Then we'll go into linear programming. And linear programming in some sense is easier because all the functions are linear, and linear things are quite simple to work with. It turns out in business, most of business is very simple. Most of the time you have linear functions. Quite frequently they're linear functions. You make more things, you earn more money. You make more things, you need more people, and so on and so on. And often those are very proportional to each other. Okay. Now what makes this more difficult is you have more than one variable, right? In many business applications, you have 10 variables, you have 100 variables, there's 1,000 variables. So there's 1,000 things you have to decide on what to do. And even more interestingly, in business applications, you have constraints. You're always facing constraints in business. You have a limited number of people, you have limited capital, you have limited technology, you have limited intellectual property. And the big question is, how do you most efficiently use those resources to your best benefit? Okay. And that's where the real interesting part comes in business management. Okay. Now, you can also add other things to your constraints. For example, you might have a constraint about how much you can pollute. If you don't want to emit greenhouse gases, you can put that in, and you can see how that will impact something like your profitability. Or if you're concerned about social issues like diversity, equity, and inclusion, you can try to put those in the model. They may be hard to measure, but you could try to measure them and put them in your model. Okay, so today it's just a very simple example with advertising. And what we want to do is select our advertising expenditure to maximize your return on investment. So what you got to think about with return on investment is the value of advertising, hopefully, is that it increases sales, right? Hopefully by advertising, you can make more money. And so the return on investment just tells you how much more money are you making relative to your cost of advertising. So you're looking at the lift of sales, right? How much more would you make with the advertising than you would make without the advertising? That can be hard to measure. With online ads, it's a little bit easier. So companies have a better handle on that with online ads because they know who buys and who doesn't buy and things like that. So in this very stylistic example, let's suppose we know what that return on investment function is, right? So you can obviously see it's a quadratic function. Now, return on investment for advertising has diminishing returns, right? So you can think about one goal of advertising is to let people know about what your product is, where your brand is, where it's positioned, what are its unique features, how does it match up to your needs, consumers' needs and wants, and all of those kind of things, right? And so if you can imagine when the iPhone first came out in 2007, people had no idea, right? They're saying, what's Apple doing making an iPhone? I love their iPod, I use their Macintosh computers and so on, but what's this thing with an iPhone? They don't make phones. So back then in 2007, Apple had to do a lot of advertising to let customers know what this iPhone is, what it can do, why they should go out and buy it. And so you can imagine the early days, they did a lot of advertising and they saw a big sales lift, right? As people became aware of just how wonderful this product is, you have a big sales lift. But today they don't advertise so much. And the reason for that is everybody knows, right? Everybody knows that the iPhone is the most delicious thing out there, and they just go out and buy it, right? So there's no need to advertise so much. I mean, they still have some advertising, but not like in 2007. And so once your market becomes saturated, everybody knows about it, right? Just advertising more and more, even though everybody already knows it, has no benefit. And when that happens, you have diminishing returns for advertising, and then your return on investment comes back down. You're advertising more and more, but your sales aren't going up, so return on investment takes a dive. And in this very stylistic example with this quadratic, that's what we have. Because when we're not advertising much at all, people don't know what this thing is, and you're not going to have very, very big return on investment. On the other hand, once the market becomes saturated and you keep advertising more and more, you overshot it, and your return on investment goes down. So obviously this is a very simple function. You say, hey, why don't you just go ahead and plot it? And obviously you can see advertising expenditure should be $10 million, right? You can see right down there, $10 million. That's where I get the most bang for my buck. Now, the real challenge in business application, though, is you don't have such simple functions with only one variable so you can plot them. So plotting it and looking doesn't scale up, right? So even with advertising, often you're advertising for more than just one product. You're advertising multiple products, and you're often using multiple media. You have online ads, you're using Facebook, you're using Google, you have regular TV ads, you have print media, you might still have radio ads. So you have all these different media, you have a different return on investment curve for all these different media. And so your decision isn't how much you should advertise, but how much should you advertise for each product and each media. And in that situation, you can't really just sit down and graph the things and try to figure it out. So what we're going to do here is plotting it works in one dimension, one x variable. It doesn't work when you have 10 x variables. It's hard to visualize. And then you have to rely on mathematics, right? I know lots of people are triggered by math, okay? But math should be your friend because it can do things that your eyes can't do. And, they can be very useful. So you might think, hey, this is a new product. Don't want to spend a lot of money, don't know if it's going to be a hit or not. Let's just kind of have sort of low amount of advertising to see what happens. Let's advertise $2 million. You say, hey, you have to negotiate with your chief financial officer to get that budget, get your $2 million. And it comes back at the end of your, hey, you had a return on investment of just about 5%. Your CFO is extremely happy with you, right? One of the biggest jobs of the CFO is to get the money you need to do your job, right? Which is fine. The CFO is more than happy to do that. That's in their job description. But the thing is, you got to pay them back, right? They're only happy at the end if you have a positive return. And here we do. So yeah, they're pleased with it. And so you go back and say, well, could we have done better? All right, could we have done better in this situation? And let me move down here for right now. And you can say, yeah, well, how could we analyze it? Well, the methodology we're kind of getting at here, it goes by different names, but it could be first attributed to Newton and Raphelstin or steepest ascent method. But what you do is imagine this is a hard curve. The blue curve is hard to understand. So you replace it with the red curve, and the red curve is tangential when x is equal to 2. That means it just barely touches the blue curve when x is 2. Okay, so the red line is above the blue curve, and it just touches the blue curve when the ROI curve when x is equal to 2. Okay, and then using that, we could use as a guide, right? So again, this is a methodology that scales up to more than one dimension. And so you can say, well, what should we do? Should we increase advertising or decrease advertising? Say, well, if we decrease it, well, the slope is positive. So if we decrease X, then we think probably our ROI is going to diminish. And that's not something that we really would like to happen. So you could say, okay, well, let's go ahead and increase X. So, oh, that looks like there's a big bang for the buck in that direction. So let's go ahead and increase it. That's brilliant, right? So you go to the CFO and say, hey, I made you $5 million, 5% return last year. Let's go ahead. I think we can do better with more advertising. This is why. And the CFO kind of likes you because you made money for the company. So you say, yeah, sure, we'll increase your budget. Let's move it up to 6 million. You say, wonderful, wonderful. And sure enough, you move it up to 6 million, and now your ROI is pretty fantastic. 12% return on investment for advertising. Wow, the CFO really liked you last year. Now the CFO really, really loves you quite a bit. You're going to be great friends with each other. And you say, well, could we do better? And yeah, the red line, the tangential red line is still pointing up, positive slope. It's not as steep as before, but still pointing up. So yeah, we can go ahead and increase your advertising expenditures. Let's go ahead and increase it to 9 million. So, okay, wow, okay, you made even more money for us, 15% ROI instead of around 12%. So, wow, you're going to be really, really, really popular in the company. And they say, well, okay, 9, can we do better for next year's budget? You say, yeah, I want to do better for next year's budget. Maybe I can get even more money. But now your slope is a little bit getting pretty flat there, right? So if you increase it, well, you're not going to get that much bang for the buck. And so I say, okay, let's go up to 10 million. And what can we do for next year's budget, right? Can we increase the budget or not? And that red line becomes flat. And you go, oh, if I increase or decrease, it doesn't look like anything's going to improve according to the red line, right? But, since you're good friends with this CFO and you've been so good to the CFO over the last few years, the CFO says, oh, I'll be nice to you and I'll increase your budget for next year. So let's go ahead and push it up to 14 million. And now when you push up to 14 million, your ROI went back down to 12%. And now the CFO is saying, oh, I like the 12%, but I really like that 15% figure from the previous year better. I say, well, can you even do better than that, right? So if we increase it even more, no, now you're even doing worse. So that's not a good idea. So we're going to go back to the 10 million and I'm going to set your budget back to $10 million. Okay. And then you go back to the 10 million, right? And that's where the optimum is. Now, again, if you have such a simple function as this, you could just plot it. You don't need to really think about it. You can just look at it and decide what to do. But again, with more complex functions and a lot of variables, the option of plotting it and looking at it isn't feasible. And so these math techniques do scale up, right? And some of these math techniques are the basis of a lot of software that you use in business, even if you don't realize you're using that software and it has these kind of methods in it. So at the $10 million, nothing changes in the environment, which is, not true of any business environment. That's where you want to be, right? But of course, you have competitors that are constantly doing things to disrupt the environment and disrupt you and knock you off the perch. So, you're always going to be moving around with your advertising budget. Okay, so where'd this come from? Well, actually, do you know your 17th century mathematics? I just love that. If you look historically, at what time period is your math up to? So if you know calculus, 17th century mathematics. If you know some algebra, if you know what a line is or a quadratic function, so on, then around 1000 AD, right? Algebra is Arabic for algorithms. And so, if you know a little bit of simple algebra, you're comparable. You'd be state of the art in around 1000 AD. And if you know a little bit, all you know is some geometry, what a square is, what a circle is. If you have a cognitive capability test where it has circle, square, triangle, and ask you, hey, which one's a circle, which one's a square, which one's a triangle, then you're about 500 BC or so. That's state of the art for 500 BC. Or earlier. So, with calculus, 17th century, our two buddies down there, Sir Isaac Newton, and at least in the English system, is credited for coming up with calculus. Leibniz also worked on it, but Newton claims that Leibniz came for a visit to London and saw his unpublished manuscript and went back and stole it, which I don't know if that's true or not, but that's the claim that Sir Isaac did. I just love that picture of Sir Isaac. I could just see him any place in New York City or San Francisco hanging out at a cafe. Just that wild bohemian look to him. He was quite a character. He was very big in alchemy. Leibniz did alchemy too. That was a forerunner of chemistry. So they were trying to turn lead into gold. Okay, that didn't quite work out so well for them. But anyway, so what you can do is you can take the first derivative of return on investment, set equal to 0. That's the slope of the tangent line is the first derivative, right? So that's just pretty simple. You don't have to be a genius like Sir Isaac Newton to start working with things like that. And then you solve for x. You say x is $10 million, and that's what we would have had. Well, this has nothing to do with constraints yet, right? So where are the constraints in this problem? Hey, you talk about constraints, but there's no constraints. So let's say your budget constraint $7 million. Okay. Well, obviously you can see your ROI is still increasing up to x going up to $7 million. So obviously you're going to spend your entire budget constraint, right? So if the CFO gives you $7 million to spend, you're going to spend the $7 million. Okay. Pretty easy. You don't have to go to a fancy business school to figure that out. And if your budget constraint's $15 million, well, this is a little bit different, right? So $15 million is beyond our optimal value. Our optimal value is $10 million. And if this was an ideal world where everybody's ethical, empathetic, and caring for each other, you'd say, hey, thank you, CFO, for the $15 million, but I'm only going to spend $10 million. And you say, okay, I'll spend $10 million. That's the best we could do. The $15 million is non-binding. It's not a constraint for you at all because it's not binding. It doesn't affect what you would do anyway, right? And so, your slack here is 15 minus 10 is 5 million. So you have a slack of 5 million. And it'd be really wonderful, right? If the CFO say, hey, thank you for saving us $5 million. I will give you 1 million, right? And if the CFO was so charitable as doing that, I'm sure people would have gone with the 10 million instead of the 15 million. But in reality, what really happens is if your budget's 15 million, you spend 15 million, right? Because if you don't spend it in the next year, the CFO says, hey, you only spent 10 million. I'm only going to give you 10 million. And then you're going to start to feel cramped, right? It's going to cramp your style. And you say, oh, I don't want my style cramp. I'm going to spend my entire $15 million budget. Won't be the best thing for the company, but hey, it makes my life easier to have more money to spend than less money, right? You're never going to say, hey, I don't need that money. I'll just go ahead and spend it. Why bother wasting on something like product development or operations or something else? Better to waste it on us in marketing, right? So that's the world dynamics, what happens in organization. So if you don't use it, you lose it, right? So your slack will be gone next year if you don't spend it. Okay. Well, hey, so super. Thanks for sticking with the video. I hope you got a little bit out of it. Next time we'll go with linear programming. Again, this is, we'll start to introduce more variables than just one. We'll make the big jump up to 2 variables. The reason for doing 2 variables is because we can graph it, and we'll look at the graphical solution. And you can get a lot of insight from the graphical solution. And then when you go up to 10, 20, 30, 50, 1,000 variables, that kind of insight's still valid, right? It still holds, even though what you learn from 2 will scale up to a higher number. Now, the only other trouble is that you have to rely on software to compute the solution for you. You can no longer put your eyeballs on it and figure it out. And then the really interesting thing, as I said before, with linear programming is the constraints. Again, with business, you always have those constraints that you're dealing with all the time. In life, we have constraints we deal with all the time, right? And so the constraints are where a lot of the interest is. Okay, great. Thanks. If you like this video, please give a thumbs up, leave some nice comments, and I hope to see you in the second video. Bye now.